subscribe now and press the bell icon. Never miss an update.
In the last class, we have considered two spherical mirrors, concave and convex. And kindly recollect that a ray of light traveling parallel to the axis of either the spherical convex mirror or the concave mirror, after reflection, obeying the laws of reflection, always passes through F. All rays traveling parallel to the axis of a spherical mirror after reflection pass through the focus. Then, a ray passing through center curvature. Remember, spherical mirror is a part of a sphere. Line joining the center to any part of the sphere, any point of the sphere is always normal. Therefore, ray passing through C is incident normally, which means I is 0. Therefore, R is also 0. That is, a ray passing through C retraces its path. So remembering these two forms, a ray passing through incident on the mirror parallel to the axis passes through F. A ray passing through C falls normally, retraces its path. So you are taking these 2 points into consideration. We keep the object, extended object. In fact, we can trace the position of the image even for point objects. Now for extended object, see, we locate the image as follows. To begin with, the object is placed at infinite distance. Infinite distance. See, the source is at infinite distance. Convergent rays, divergent rays traveling infinite distance become parallel. Therefore, they all pass through F. The extreme point, another extreme point, convergent, divergent rays. See, traveling infinite distance become parallel by the time they reach the mirror. Therefore, they converge to a point, not at F, but at a point just below F. That is in the focal plane, the so-called focal plane. And therefore, we have taken 2 rays. Rays from the lowest point, the topmost point. Instead of what is true for this point and this point is true for all the points. Therefore, we simply draw the perpendicular from F, the foot to the top. So this gives the image at F. And it is real, which means you can get it on the screen. It is diminished in size, smaller in size, and it is inverted. Next, I bring the object closer. Keep it beyond C. As before, a ray parallel to the axis passes through F. A ray passing through C retraces after reflection normally. The 2 rays meet here. Therefore, this is the image of the point B. And as this is placed at right angles, I draw a perpendicular here from here to here. Therefore, this gives the image. Notice that in this case, the image is between F and C. It is real because the rays intersect. It is inverted and it is smaller in size. Diminished. So we continue. Notice here, this is a special situation wherein object placed at C, ray parallel to the axis, again passes through C. Ray passing through reflects. See, it is imagined that the mirror is like that, so it falls normally, retraces, and therefore you have the image at the same place. Now, image at the same place image size is same as that of the object and it is real inverted. I move the object towards the mirror. See, I find the image as before. Beyond C, it is real, enlarged and inverted. For the first time, it is enlarged. Now, at F, see, rays from the object and the reflection become parallel. That means the rays meet at infinity. Parallel rays, we say that mathematically meet at infinity. And at infinite distance, we do not know the other details of the image, whether it is inverted, same size, bigger size, something like that. So we only know that it is at infinite distance. And this is a special situation where the object is placed between the pole, that is the mirror, and the focus. As before, we have taken two rays from P. One is parallel to the axis, passes through F. Another incident normally comes back. They do not meet in front of the mirror. When produced backwards, they meet here. And draw the perpendicular, that is the image. Notice that, see, the image is behind the mirror, as in the case of a plane mirror. As in the case of a plane mirror. It is virtual for the first time. It is enlarged. It is erect for the first time. So this is the various positions of the object in front of a concave mirror and corresponding image positions. Notice in all these figures, the real image is inverted. The virtual image is erect. Now all of them I have put here. Notice I start from here, I travel towards the object like that. See, the image appears for the first time here at F. As you move towards the mirror, the image moves away from the mirror. For every position of the object, there is a corresponding position of the image. For every position of the object, there is a corresponding position of the image. If I move further towards the mirror, now suddenly what was here appears here. Now what was real appears as the virtual image. Wherever you keep the object in front of it, see, there is a corresponding image position. So we distinguish, see here, as I indicated, these see the region where you have the image formed. We never get the image here between P and F. In the case of concave mirror. Anywhere else you get, either behind the mirror or in front of the mirror, except in this situation. Except in this situation, we don't have the image formed. Now come to the convex mirror. It looks as if that's a complement of this. Now keep the object in front of it, as in all these cases. I don't have to take separate situations. In general, you can keep anywhere here. A parallel ray reflects again, obeying the laws of reflection, eye is on, passes through, appears to come from F. Another ray falling normally, retraces its path. The two reflected rays, when produced, meet here, draw the perpendicular, you have the image. You have the image. Notice that wherever you keep the object in front of the mirror, the image is always here. This is what we call image space. Where we don't have here this image, it is only in this forbidden region we have here. Now we never get images here in the case of a convex mirror. You can keep anywhere. This is the object space, this is the image space, restricted. Now, you consider here this formula which we have derived in last class, 1 over B plus 1 over B. Now the first figure, if the object is at infinity, see what happens. 1 over infinity is 0. 1 over f is 1 over v. Now because f is negative, so v you have here. So that is what we have got there. Object at infinity, see if u is at infinity, v is at 0. And another case, see if the object is at, let us suppose, if you keep the object at here, see what happens. 1 over f equals 1 over v, 1 over f, it is minus f because of sign convention, and this is also negative. So therefore, if you rearrange, 1 over v is 1 over f plus, this becomes 1 over f plus 1 over f minus, therefore this is 0, therefore v is 1 by 0, which is infinity. This is what we have. Now if you practice these figures, you can know the answer in a problem without solving it, because you know if you keep the object at some position where you get the immediate plot. Now, we'll go on to another topic, refraction of light. We have seen that in an isotropic optical medium, light propagates in the same direction. This is known as rectilinear propagation of light. Now, if you have, this is optical medium 1, we have another optical medium 2. You can imagine air, water in a beaker, like that. So as long as the medium is same, light travels in the same direction. Now if it changes the medium of propagation, it is found that generally, see, it does not go in the same direction. Does not go in the same direction. It is found to change the direction of propagation. Direction of propagation. Once again, light in an optical medium, isotropic optical medium, travels the same direction. If it changes the medium of propagation, it is generally found to change the direction of propagation. Now this property of light, by virtue of which it changes the direction of propagation, is called refraction of light. Now you can think of an analogy, mechanical analogy. Say for example, you have water. You have water. And if you drop water, a stone, we find the stone drops down vertically to this point. Instead, if you throw the stone like this, it is our experience, you can try, it never goes here. It never goes here. It is always going like this. So, even in the case of a particle, material particle, when it changes the medium of propagation, it is going in this medium, now it is going in this direction, see, like that. So, we have this situation here. Now, whenever refraction takes place, we come across the following terms: x, y. Plane of refraction. in the plane where refraction, that is this change. Now this change takes place only at this point, at this plane. Therefore it is plane of refraction. Now ray in the first medium. Ray in the first medium is called incident. Ray in the second medium is called refracted. The point where the incident ray meets the surface, it is xy is the surface, remember, like this. So a ray like this, it's a line, they meet at a point. So Y is point of incidence. Point of incidence. The point where the ray falls. Point of incidence. You can always draw a normal that is perpendicular to the surface at the point of incidence. That is normal to the plane of incidence xy at the point of incidence O. Now that makes, see, the normal makes two angles here. Angle with the incident ray, the normal makes an angle with the incident ray, that is called angle of incidence. The normal makes an angle of refraction, angle of refracted ray, the angle of refraction. So here you have angle between incident ray and the normal. It is the angle of incidence. And similarly, angle BOM, angle between the refracted and the normal, angle of refraction. Notice this. This is incident ray direction, refracted ray direction. The directions are different. They make an angle between them. This is the deviation. This is deviation. We will denote it by angle. So angle between the incident ray produced, AO produced to C, refracted ray OB. This angle is the difference between these two angles. Now in this case, see, it is I, this is also I, because vertically opposite angle, and therefore this much is I minus R. In general, it is I difference R, the angle of deviation. Angle of deviation. Now, why does this bend like this? Now, remember the example that I gave you. See, if a stone is thrown, let us suppose, into water in a direction like this, it would not go like this, it would go like this. The reason, as you can expect here, is the stone experiences less opposition here, more opposition here, opposing force, frictional force as we call it. In other words, the velocity of stone, if you drop straight like this, is more in this case, it is less in this case. Now this difference in velocity causes the change in direction, that is refraction, the same reason. So the cause of refraction, is change in velocity of light. in different medium. In different medium. Now, see, whenever light goes, see, you can make light go like this, like this, like this, like this. For every incident, there is always a refracted. We have these angles. We define, or refraction takes place, obeying certain laws. Now, the first law is the refracted ray lies in the plane of incidence. Lies in the plane of incidence. Now this is similar to the first law. Now let us suppose, the other day if you remember what I see, if you have a point, draw a line, you can draw infinite lines. If you have 2 points, you can draw only one line. In other words, 2 points decide a line. Now similarly, if you have a line like this, if you have a line like this, if you have a line like this, let's suppose, draw a plane passing through it. Now this is one plane, this is another plane, this is another plane. Infinite planes you can draw. Now if you have 2 lines, let's suppose one here and one here. If you have 2 lines like this, draw a plane passing through these. There is only one line. That means one line doesn't fix a plane, but 2 lines fix a plane. So you have defined the plane of incidence here, the plane of incidence here. The plane of incidence means the plane containing the incident ray and the normal. So this is plane of incidence. So only in that plane, see, if you imagine this is a tank of water, if light enters here, now it goes into water, not like this, but only in this particular plane. Then, the second law, more important law, it is also called Snell's law. Snell's law of refraction. Now here, if light comes like this, enters like this, just as the stone drop, it would go like this. If it comes like this, only it doesn't go like this here. It doesn't go like this here. See, it doesn't go like this. So it is I0 here, I0. You can take any incidence except this. So with this restriction, say for oblique incidence, that is incident at an angle not equal to 0. The ratio of the side of the angle of incidence to the side of the angle of refraction is always a constant. It's always a constant. Now, the significance you must know. See, you are free to change I or adjust such that this ratio remains constant. It is something like Boyle's law. If you change pressure, volume changes. But the product of pressure and volume remain the same, provided the temperature remains constant. Similarly, this is constant, provided, say, for the given color of light, I have not mentioned there, I have just mentioned it is light. It may be red light, blue light, green light, like that. Different colors. For a given color, more appropriately, for a given wavelength. And for the pair of medium, the given pair of medium. Now what I mean is, see, if you have, let us suppose, light going from air to water, let us say, this is air. It is going like this. Now water, it deviates. Instead, if it is glass, it deviates like this. So if you change the medium, for the same angle of incidence, the deviation is different. This is the deviation, this is the deviation. So that is what is the condition to be followed here. Now this constant is called refractive index. Of the second medium with respect to the first medium. Refractive index of the second medium with respect to the first medium. Now that means you must specify, say, what is the ratio of cyanide to cyanamide? Refractive index of water with respect to air. Refractive index of glass with respect to air. And if you take, let's suppose, water and glass like this. Now this constant is different. If you change the medium, that is what it means here for the given pair of medium, for the given color. So if you have, let us suppose, same medium, air and glass, same angle of incidence, I. See, one light, for example, green light deviates like this, blue light deviates like this. I mean, red light. So if the color changes, deviation changes. This is the original direction. Deviation is less, deviation is more like that. So we have to specify the medium. So it is called refractive index of the second medium with respect to the first medium. Denoted by the rectilinear. While reading, refractive index of the second medium with respect to the first medium. Now it's an index, refractive index. This index finger, it shows you, see, in algebra, this is index. It indicates something. Now what is it? A is multiplied by the base is multiplied by itself 3 times. Similarly, this index is the index of refraction. What is refraction? This is refraction. Now if you have smaller deviation, n is less. If you have greater deviation, n is more. See, for water-like substance, see, it is 1.33. For glass, it is 1.55. Say for diamond, it is 2.4. So this indicates how much it deviates. So we have refractive index or the second medium with respect to first medium is sin I by sin R. This is mathematical form of the second law, Snell's law. What are the conditions to be followed? See, I should not be 0 because if I is 0 or is 0, it becomes 0 by 0. We don't have the meaning for that. And same color applicate. You must not change the color. And same pair of medium. Like that. Now, see this, because related to this, say with respect to, it's also called relative refractive index. Now, absolute refractive index. Absolute refractive index. See here, whenever light passes, given medium, optical medium. See, we fix this, it is free space. Commonly, practical. For all practical purposes, here. See, whenever light passes from free space into the given medium, then finite is on, or it's called absolute refractive index. So, N, see, of the medium, here there is no medium. Free space is no medium. It may be free space or vacuum for all practical purposes here. So that we call it, whenever light passes from this medium to this medium, that is from vacuum to the given medium, this is called absolute refractive index. Next. See, I mentioned the cause of why does this happen? Because velocity here are different. Now we can also define refractive index in terms of velocities. Since refraction is caused by, is due to the difference in velocities. Of light. See, refractive index can also be defined in terms of velocities. In terms of velocities. For example, let us consider let c be the velocity of light. In free space, in vacuum, in the air. V1 be the velocity of light. In medium 1. V2 be the velocity of light in medium 2. Now look at this. Now this is refractive index of the second medium with respect to the first medium. Refractive index of the second medium relative to the refractive index of the first medium. So here I can write using these two relations. Say absolute refractive index. Absolute refractive index of medium 1 is refractive index of the first medium. Is not this. Here we don't have material medium. It is medium free space. So this is free space. So here sin I by sin R. Always I is here, R is this medium. The second medium, see we have R. Absolute refractive index of medium 2 is N2 equals sin I by, with respect, N2 is sin I by sin I. Like this. Therefore, dividing one by the other. Dividing, let us say N2, then dividing N2 by N. Like that. Is equal. Now this is sin I by sin R divided by sin I by sin. So that gives you 1. Now instead of that, I will make use of the relative refractive index. I'm sorry. Say, first I will define relative refractive index. Refractive index, that is relative refractive index of the first medium of the second medium with respect to the first medium is equal to N2 with respect to 1. It is V1 by V2. I will call this equation 1. Now, absolute refractive index, I define it like this in terms of velocities, not in terms of angles. Absolute refractive to the medium N1 is equal to C over V1. Absolute refractive to the second medium N2 equals C by V. Therefore, dividing, we get N2 by N1 is equal to C by V1 divided by C by V. And N2 by V. Now that gives us V2 by V2. So that is, see, if you take the reciprocal of this, that is how you have N1 with respect to N2, 2 is V2 by like that. Either this or this, you can write in both the forms. But V2 by V1 is refractive index of the first medium the second medium with respect to the first medium. Therefore, you have this relation. Say N2 with respect to 1 is N2 by N. N2 by N. Now, you can combine these relations. See, definition of refractive index, ratio of sine of the angle of incidence to the sine of the angle of refraction. Now in terms of velocities, V1 by V2. V1 by V2. Now, in terms of refractive index, absolute refractive index, N2 by N2. And we have seen that we know that light is electromagnetic nature. So wave means we always associate wavelength. So this is also equal to lambda 1 by lambda. So these are the various forms of Snell's law. Various forms of Snell's law. Now all the paths. See, we consider these two always. That is, N1 sin I is equal to N2 sin I. That is the form in which we usually use this relation, and we apply this in several situations. Now, consider these two relations, sin I by sin R, as being equal to V1 by V2. Now here, when two media are there, see, if the velocity in the first medium is more than the velocity of the second medium, like this. See, if V1 is more than V2, then V1 by V2 is greater than 1. Now that is sin I by sin R is greater than 1. Or sin I is more than sin R. In other words, I is more than. So if a situation, let us suppose, if light entering from one medium to another medium, like this, I is more than, or it doesn't go like this, generally it goes like this. So here R is less, I is more. Now this medium is called tensor medium, optically tensor medium. This is optically level. That means refracted, it deviates towards the normal. If light passes from rarer to denser. Now, again, from sin I by sin R is equal to V1 by V2. Now, if you have a situation where light is going like this, light is going like that. So V1, if V1 is less than V2, then V1 by V2 is less than 1. That is sin I by sin R is less than 1. Now that means I is less than R. So if light is going like this, it doesn't go like this, it is going like this, away from the normal. The normal is here. Now in this case, R is more, I is less. Now this is tensor medium. So you have to remember that when light passes from rarer to denser, it deviates towards the normal. When light passes from denser to other, it deviates away from the norm.
Subscribe now and press the bell icon. Never miss an update.